Hello everyone, my name is Guoping Ruan. Today I'm going to give you a presentation on our research, which is called Comparing Spatial-Temporal Models for Aggregate PV Power Nowcasting. I have divided this presentation into 4 parts. Firstly, I will give an introduction of our research. Then I will show you the methodology we have used. After that, the experimental results will be delivered to you. Finally, there is a conclusion for our research. Because using fossil fuels, the environmental problems are worsening. People now promote to develop renewable energy, especially solar energy. However, passing clouds could cause PV power fluctuations. For this figure, we can see that the blue curve is the clear global horizontal irradiance, and the yellow curve is the measured GHI. Therefore, if we directly integrate this PV power into grid, will cause grid frequency deviations, even blackouts. To solve these problems, there are 2 methods. The first one is using energy storage system, which is termed as reactive approach. However, with the scale of PV power system increasing, the cost of energy storage system will be very high. Therefore, people turn to using solar forecasting, which is termed as proactive approach. Based on time scale, it can be divided into 4 classifications. For instance, each minute, each hour, each day, and day ahead forecasting. The each minute forecasting is also known as solar nowcasting. And there are 2 methods consisting for solar nowcasting, which are sky image and sensor network-based approach. For sky image-based approach, it aims to extract the cloud motion vectors. Error comes when convert cloud conditions directly to ground irradiance. These problems can be get around by sensor network-based approach, such as cloud height approximation and peak irradiance conversion. Currently, studies on solar nowcasting only focus on point forecast, which means that the target is only a small system or a single sensor. If aggregated power systems are considered, the geographical smoothing effects can significantly affect the correlations between the sensor data and the focal system. Therefore, the relationship between sensor data and focal system for aggregate PV power systems are unknown. Our research aims to investigate the performance of spatial-temporal nowcasting models on aggregate PV systems. The data we used are from Oak Solar Measurement Grid, which is a irradiance sensor network installed by National Renewable Energy Laboratory. From this figure, we can see that the DH5 is selected as a predictor, and the downwind sensors are selected as the focal system. Here are the nowcasting setup for Chen test set. It has n rows and p columns for the features. The n is the number of samples, and p is the number of temporal predictors. There are 4 nowcasting models, which are linear regression, ridge regression, lasso regression, and long short-term memory. These 3 are the formulas for regression coefficient for regression family. Here are the details of the LSTM block. For our LSTM model, we have 2 layers. The units for each layer are 80 and 12 respectively. To compare the performance of these models, we have used several error metrics, which are normalized mean absolute error, normalized root mean squared error, and the forecast scale. For FS, we compare our model with the persistent model. Here are the formulas for these 3 error metrics. And we have conducted 3 case studies. For the first one, the forecasting horizon is fixed at 60. The number of temporal predictors are changing from 1, 10, 20 to 60 for the focal system, which is aggregated by 3 sensors, DH6, DH9, and DH10. Let's look at these 3 figures. we can see that the NMAE and RMAC for regression family are decreasing with the number of predictors increasing. And they can get the best FS when the number of predictors is 60. For LSTM, it can get the best FS when the number of predictors is 10. For the second case study, based on previous one, we set the number of predictors for regression family as 60. For LSTM, it should be set as 10. And the horizons are changing from 30, 60, 120, 300 seconds. They are for the same aggregation system, DH9, DH6, and DH10. From this figure, we can see that NMAE and NRMAC for all models are increasing with the horizons increasing. And for regression family, they can get best FS when horizon is 30 seconds. For LSTM, it is 60 seconds. And the last case study, based on the previous case studies, we can set the number of predictors for regression family as 60, and for LSTM, set as 10. In addition, the forecast horizon is fixed as 30 seconds. We change the aggregation area from set 1, set 2, and set 3. From these three figures, we can see that the NMAE, NRMC, and FS of all models are decreasing with the aggregation area expands. Our study is a comparing study on the performance of spatial-temporal models for aggregate PV power nowcasting. After we conducted 3 case studies, we found that the forecast scale of all models can decrease with a larger temporal predictor set, longer forecasting horizon, and a larger aggregation target. For solo nowcasting, even simple regression methods can achieve satisfying accuracy with few training reinforcement, as long as the spatial-temporal predictors are adequately used. And the nowcasting difference between regression family and LSTM is observed to decrease as the PV aggregation expands. Therefore, the spatial-temporal regression is highly competitive for practical aggregate PV power nowcasting. And that's all. Thank you.